Okay, so we have discussed about the physics of the degenerate stars, what happens, how we can say that degenerate pressure basically means greater pressure compared to classical Maxwell-Boltzmann pressure, right, for electrons. Now let us start with the non-relativistic degenerate electrons. Let us start with that. Now for that, let us consider a gas at 0 temperature, 0 Kelvin. Then what happens as a result? This means that all electrons have the lowest possible energy. আচ্ছা দাঁড়াও, হ্যাঁ ঠিক আছে, yes, so I am considering non-relativistic degenerate electrons, right? So let me consider gas at T is equal to 0 Kelvin, which means all electrons have the lowest energy, right, possible without violating Pauli's principle. This is important. We cannot violate Pauli's principle, right? Now let me consider equation 7. Then from there we see for complete degeneracy we have, you see, this distribution, which will be given by equation 26. Now note that this distribution function is not continuous and all momentum cells below a certain value Pf. So all momentum cells below a certain value Pf are occupied and those above are empty, right? As a limiting value Pf, this is known as Fermi momentum. Okay, now the energy, the energy corresponding to the transition region is the Fermi energy. Which is EF equal to kBT. Now the electron distribution is given by equation 23, which we have just discussed previously. You must remember. What was equation 23? Do you remember? This was equation 23. Right? Now, so we have, considering this, we have now this new distribution, which is equation 27. Okay, now what about the total electron density? So the total electron density, let me write it down. This is basically given by this relationship over here. So this is equation 28. And then the Fermi momentum. So Fermi momentum, তোমরা এই ক্যালকুলেশনস গুলো একটু নিজেরা চেক করবে। আমি এখানে ডিটেইলসে যতটা পেরেছি I have shown you, but I would like you to check these calculations as well, at home. So the Fermi momentum, you see, is given by this relationship using this Ne over here. This is equation 29. That is, for a given energy, for a given electron density, you see, this Fermi momentum Pf is proportional to Ne to the power 1 by 3. Right? Now, what about Fermi energy? We can easily obtain this, right, using the relation P square by twice Me. Why? Because we are considering the non-relativistic part, right? So this is the Fermi energy. Equation 30. So this is Fermi energy. Now, let us take an example. Suppose T is equal to 0 and Ne is equal to 10 to the power 28 per centimeter cube. Then from here we get Pf is equal to 7 into 10 to the power minus 18 gram centimeter per second. You calculate this thing. You check that this is indeed correct. And as a result, Ef is equal to 2.7 into 10 to the power minus 8 erg. Now, since we know that the value of, you see, MEC square is equal to 8.2 into 10 to the power minus 7 erg, which is basically 0.51 MeV, তাহলে এইখান থেকে আমরা পাবো যে EF, we will see that this is much greater than MEC square. So this characterizes, so this means this case of T is equal to 0 and Ne is this characterizes the non-relativistic case. Okay. Now, in order to obtain the pressure, electron pressure, in order to obtain electron pressure PE, we use equation 11. Now, in non-relativistic case, we know that P is equal to Me into V, and as a result, you can see that you can write down the P like this. Here, this is equation 31. Now, if we use the previous equation using equation 29, then you will see, and this equation, then you will see we will finally have this, which is equation 32, and this is the equation of state for a completely degenerate non-relativistic gas. Now it is important to note that PE is independent of temperature, as I was telling you before from the graphs. Remember? Now the transition, this is important. You see, the transition between degenerate and non-degenerate gas, it can be obtained. Let me find the transition region, right? It can be obtained by equating, you see, equation 32 with the pressure equation, basic equation of pressure. And what is that? Tell me the very basic form that we all know, which is P is equal to NKT or KB rho T by mu into MH. Now you understand this part, right? Now we are going to find the transition region between non-degenerate gas, which is this part, and degenerate gas, which is equation 32. So the region between, we want to talk about it. So, and for that we have to equate the two equations, and upon equating we get that if we do this with putting n is equal to Ne, then if we do that, then we see that degeneracy occurs if rho is greater than 2 into 10 to the power minus 8 T to the power 3 by 2 gram per centimeter cube. This is important. I would like you again to check this yourself. Now before I end today's class, let me just take an example. Again, an example. These examples are important. Say for example, I can give you this example in a numerical form in the exam. So say in the solar interior, let us take rho of the order of 10 square gram per centimeter cube and temperature of the order of 10 to the power 7 Kelvin. So from here we have 2 into the previous relationship, 2 into 10 to the power minus 8 T to the power 3 by 2 is of the order of 600. How much is this? 600. Now this is greater than 10 square. So this means this condition, which name is say equation 33. So equation 33 condition is not fulfilled, and we can say that there is no degeneracy. Now let me this was example 1. Now let me consider example 2 in a white dwarf. Right. Now in a white dwarf, suppose the density is of the order of 10 to the power 6 gram per centimeter cube and temperature is of the order of 6 Kelvin. Then you will see that this 2 into 10 to the power minus 8 T to the power 3 by 2, this comes out to be 20, which is much less than 10 to the power 6. So this means that equation 33 is satisfied. So this means that white dwarf is degenerate. So you can say that this equation 33 shows us an approximate way the transition between a non-degenerate and degenerate gas. So it shows us transition between degenerate and non-degenerate gas. In fact, such a transition is gradual and the electron occupation index goes from non-degenerate to the degenerate case continuously. Okay? Okay. So, till now we have considered the non-relativistic, degenerate electrons, right? And that also at T is equal to 0. Okay, so this is the case we considered just now. Next, what we are going to do is relativistic, again degenerate electrons, and again we will be considering the assumption of T is equal to 0. So this is the case which we are going to work out now. Okay, fine. Now, you see, as the density increases, what happens is that the maximum momentum, it also increases. Now, it may then happen that the maximum momentum, this corresponds to relativistic velocity. For which the relation that we have used till now, that is P is equal to MEV, will not be valid. Right? Where ME is the electron rest mass. Now, under this relativistic case, we will have to consider the relativistic expressions. Okay, so the total energy is then given by, you see, this relation, fine, which is equation 34, continuing our previous nomenclature of equations. Also, in this case, the momentum will be this, right? Equation 35. Okay. Now, also, what about the velocity? Similarly, velocity will also be this expression, relativistic expression, equation 36. Okay. Now, using, you see, equations 27, 11 and 36, these expressions, we are now going to estimate the electron pressure under the relativistic case. And you see, the result, I'll just show you the integration that we have to perform. So this is the integration that we have to do, and this is equation 37. Now, I am not going to do the integration over here, but I am going to write down the result of this integration. Well, you see, the result of this integration is this thing here. You see, pressure is proportional to some function fx right now. Now, what is fx? Right, you must be thinking what is fx and what is x. But before that, let me write down the density. So, this is your equation of state. Right, what about the density? Well, the density is, in this case, given like this. The density depends on x cube. Again, what is x? This is a new parameter which we have defined, you see, where x is this quantity, PF, Fermi momentum divided by ME by C, and you see x is proportional to NE to the power 13, equation 40, and also Fx is given by this expression here. So now the electron degenerate pressure for the relativistic case, it does not depend on the previous case simple power expression of NE, but on the other hand it depends on a very quite complicated form, as you can see. Now, numerical values of Fx can be found in Chandrasekhar's book, right? It is important to note that, you see, this equation 38, 40 and 41, they define P as function of NE. Okay, now let us see the typical values of NE. So, from these equations we find that P is a function of NE, and it's a quite complicated function. Okay, Now you see typical values are any of the order of 10 to the power 27 per centimeter cube. PE is of the order of 10 to the power 18 dyne per centimeter square. This for x is equal to 0.1, and Ne is of the order of 10 to the power 30 per centimeter cube. Okay. Okay. Now you see, as a result, and also for this and here, just a second. So typical values, one is this, another one is here. Say Ne is of the order of 10 to the power 30 centimeter cube, and PE is of the order of 10 to the power 23 dyne per centimeter square. This time for x is equal to 1. Okay, now since I am talking about the typical values, it is quite interesting to know how do this function actually looks like in the plot. Okay, so let us see the functions plot. Okay, so here you can see the function fx. How does it look like? I have shown you the plot of log of fx versus x. Okay, now moving forward, now for larger values of PE and Ne, you see x is much greater than 1, and this corresponds to highly relativistic degenerate electrons, right? You see, according to equation 40 over here. So now you see what we are going to talk about is the ultra relativistic limit, where we have this assumption. So ultra relativistic limit means here the Fermi energy is much greater than the rest mass, and you will see that under this scenario, this function fx here, this can be reduced. So you see, we don't have to consider all the terms in fx. So under this scenario of ultra relativistic case, fx becomes equal to approximately twice of x to the power 4, equation 42. Okay, and as a result of this, we get, you see, this relation for electron pressure. So this is the equation of state of an ultra relativistic completely degenerate gas, again at T is equal to 0. Okay, now you see, using a similar procedure as in the previous case, we can talk about the transition between relativistic and non-relativistic case, and you will see that this transition between relativistic and non-relativistic case, this occurs for rho is greater than or equal to 7 into 10 to the power 6 gram per centimeter cube. So we have, for this we have to equate the pressure for relativistic case and non-relativistic case, equate them, and then we will get this condition, which is equation 44. Okay, so what we have done just now is that we have seen that P is proportional to Fx, right? So in the relativistic case, we have seen that PE is proportional to Fx, right? Then we considered the ultra relativistic limit, right, which is EF much greater than ME C square, and from there what did we obtain? You see this thing. So we obtained, for this ultra relativistic case, we obtained that Fx is approximately equal to 2x to the power 4. So here Fx is of the order of twice x to the power 4, and as a result PE here is proportional to Ne to the power 4 by 3, right? Ne to the power 4 by 3. Now, apart from the ultra relativistic case, you see, just previously we talked about the non-relativistic limit, but we treated it separately. Now it will be interesting to see that if this result we can also get from here as well. Okay, it will be an interesting exercise for us. Okay, so let us try to derive the relation of non-relativistic case from the relativistic one. Let us try to derive this. So for that, we notice again that Fx is equal to x into twice x square minus 3. We can write like this: x square plus 1 to the power half plus 3 sine hyperbolic inverse x. Now we know that x square plus 1, let us do an expansion of this. X square plus 2 minus x to the power 4 by 8 plus x to the power 6 by 16 and so on. Now this expansion we have done for x square less than 1, right? Similarly, let us do the expansion for sine hyperbolic inverse x, and upon doing that we will find x minus 16 x cube plus 3 by 40 x to the power 5 minus 15 by 336 x to the power 7 plus so on. And this time we have considered this limit. Okay, so if we use these two expansions in this Fx, then you see we will get Fx is equal to twice x cube minus 3x into 1 plus x square plus 2 minus x to the power 4 by 8 plus x to the power 6 by 16 minus so on. Okay, plus 3 times of x minus x cube by 6 plus 3 x to the power 5 by 40 minus 15 by 336. Okay, fine. Now let us consider only terms in xn with n less than equal to 7. Now if we do that, then you will see that Fx becomes equal to, Fx becomes equal to 1 plus 3 by 8 plus 9 by 40 x to the power 5 minus 1 by 4 plus 3 by 16 plus 45 by 336. You can easily check this yourself. Okay, to the power 7, x to the power 7. Fine. So this means that fx is equal to 8 by 5 x to the power 5 minus 4 by 7 x to the power 7. So this is approximately equal to 8 by 5 x to the power 5. Fine. And as a result, you will see that we will get PE is equal to pi me to the power 4 c to the power 5 by 3 h cube into 8 by 5, right, into, you see, I am showing you the complete derivation for this reduction. And this again into Ne to the power 5 by 3. And so this finally gives us PE is equal to 3 to the power 2 by 3 h square divided by 20 me to pi to the power 2 by 3 and Ne to the power 5 by 3. Okay, so here what do we get? Again, so we are getting P is proportional to Ne to the power 5 by 3. Fine. So this is what we have, fx proportional to 8 by 5 x to the power 5. Right. So here we have considered, you see, in this case for non-relativistic one, right, we considered PF much less than me c square, or basically this means x much less than 1, and so we obtained fx is equal to approximately 8 by 5 x to the power 5, and from here we get PE proportional to Ne, right, to the power 5 by 3. And this is exactly the result that we previously obtained using a separate formalism for non-relativistic case. So this is a very good way to do the thing. So we did this by getting the expression for fx. So this is what we did, fx here in ultra-relativistic case, and this is the fx value for non-relativistic case. Okay, fine. Now we are going to talk about the last part, which is basically non-relativistic partially degenerate.